Hey everyone, welcome! Today we're diving into a mission that is fundamentally changing how we see our planet, Nisar. It's a really key part of our look into sound ranging and spectral imagery, so let's get right into it. Imagine a satellite that doesn't just, take pictures. Imagine one that can measure the tiniest movements of the Earth's surface, down to the millimeter. That's not science fiction. That's Nisar, a massive joint mission between NASA and ISRO. Today, we're going to break down how this revolutionary radar system is basically a global pulse monitor for our planet. All right, so here's our roadmap for this explainer. We'll start with the tech behind Nisar, then walk through its life cycle from launch to operation. After that, we'll explore its global monitoring goals, understand its real-world impact, and then we'll finish up with a quick recap to lock in all the key facts, especially if you've got an exam coming up. Okay, let's jump right into Section 1. We're going to get to the core of what Nisar actually is and the groundbreaking technology that makes it all possible. So, what does Nisar actually stand for? It's the NASA ISRO Synthetic Aperture Radar, and that name tells you two absolutely crucial things. First, it's a historic team-up between NASA and the Indian Space Research Organization. And second, its key technology is radar. But what makes this a true game changer is that for the very first time, we're going to have a satellite using two different radar frequencies, L-band and S-band, from a single platform. So how does it see? Well, it uses advanced microwave imaging. It sends out signals and then reads the echoes that bounce back. This lets it build these incredibly detailed, high-resolution 3D maps of the Earth's surface and spot even the slightest changes over time. It's pretty amazing stuff. Okay, the heart of Nisar is its dual-band system. The best way to think about it is like having two different sets of eyes. NASA's L-band radar uses longer waves that can actually penetrate deep into forests and ice, measuring things like ground deformation. At the same time, ISRO's S-band radar focuses on things at the surface level, which is perfect for monitoring crops. So having both gives us a complete picture of the surface and what's underneath it, all at once. That's what makes it so revolutionary. So how do you get this incredible piece of tech into orbit? Well, the mission relies on India's super powerful Geosynchronous Satellite Launch Vehicle Mark II, or GSLV Mk2 for short. It's an expendable 3-stage rocket, and once it gets NISAR up there, the mission is designed to operate for a solid 5 years. All right, let's move on to Section 2. We're going to look at the mission's entire life cycle, from the second it leaves Earth to the moment it starts its crucial scientific work. The whole mission is broken down into 4 really clear phases. First up, you have the launch, which is all about getting into orbit. Second is deployment, a super critical mechanical phase we'll talk more about in a second. Third is commissioning, which takes the first 90 days to test and calibrate everything. And finally, you get the main event, science operations, which is the 5-year data collection phase. Now, when we talk about that deployment phase, the scale is just mind-blowing. The antenna reflector is a massive 12 meters in diameter. I mean, to put that into perspective for you, that's about the size of a small bus. And this visual just perfectly illustrates the engineering challenge. That enormous 12-meter antenna has to be unfurled and then extended out on a boom that pushes it 9 meters away from the satellite's main body. This whole mechanical ballet happening up there in space is absolutely critical for the mission to even work. Okay, so the satellite is in orbit. It's deployed. What is it actually doing up there? Section 3 covers its global monitoring objectives, what it's built to track, and why that information is so incredibly vital for us down here. Here's a number you really need to remember: 12 days. Nisar will provide a complete global snapshot of our planet every 12 days. This creates a regular, predictable heartbeat of data, letting scientists monitor changes on our planet's surface with a precision and regularity that we've just never had before. The mission is laser-focused on 4 primary scientific goals. It tracks ground deformation from things like earthquakes and volcanoes. It measures biomass, which helps us understand forest health and carbon stock. It keeps an eye on agriculture and wetlands. And finally, it studies the cryosphere, that's our planet's frozen world, by observing sea ice and glaciers. And this brings us to Section 4. This isn't just about academic science. The data from Nisar has some profound real-world impacts. So let's take a look at how this information actually helps us right here on the ground. The applications are incredibly practical. This data is going to be used for disaster mitigation, helping us better prepare for things like earthquakes and shifts in ice sheets. It'll monitor the stability of our infrastructure and track how our cities are growing. It also helps in environmental tracking, spotting things like deforestation or even oil spills, which allows for much better resource management and data-driven planning. To really understand Nisar's power, just imagine a dense forest during a heavy monsoon. A standard optical satellite, it just sees a blanket of clouds. A better one might see the very tops of the trees. But Nisar's L-band radar, it punches right through the clouds and all the leaves to see the actual tree trunks and the ground beneath. This isn't just an improvement, it's a total game changer. All right, we've covered a ton of ground, so let's wrap up with our final section. A quick recap to consolidate everything we've learned. This is perfect for reinforcing those key concepts, especially if you're studying for an exam. If you ever need to explain NISAR in an exam, you can draw this whole thing in 30 seconds. You ready? Step 1, a simple rectangle for the satellite body. Step 2, draw a 9-meter line coming off it for the boom. Step 3, add a big circle at the end for that 12-meter antenna. And finally, draw 2 different zigzag lines for the L-band and S-band waves, pointing down to a target like a mountain or a tree. It's a super simple visual that captures all the key parts. All right, let's lock it all in with a rapid-fire recap. Nisar is a joint NASA-ISRO mission with dual-frequency radar. It's launched by the GSLV Mk3 for a 5-year mission. Its key piece of hardware is that huge 12-meter antenna on a 9-meter boom. It monitors the entire planet every 12 days across 4 key science areas, and its data is absolutely vital for disaster mitigation and resource management. So I'll leave you with a question to think about. Considering that Nisar can see right through clouds and monitor the Earth with such regularity, how might this fundamentally change the way that disaster relief teams or even armed forces respond to something like a landslide in a remote, rainy, and totally inaccessible mountain region? It's a powerful thought about the future of this technology. Thanks for joining this explainer.